used to build a deep learning model. We discussed a little bit about the general working of TensorFlow. And generally, TensorFlow has two execution modes. The first execution mode is called graph execution mode. Then other one is called eager execution mode. So the first execution mode is graph execution mode. And in graph execution mode, there are two phases. The first phase is the creation of a computation graph. So before you're going to do anything with your input data, you create a computation graph. So that is the first phase. Then you run your data through the computation graph you created in the first phase. So that is the basic two steps in graph execution mode. And the graph execution mode is a natural way of supporting so-called automatic differentiation. And so automatic differentiation, or AD, is an important feature of modern deep learning frameworks. If you did not have this feature, then you have to calculate, you have to write formulas and write your own code to calculate the gradients through differentiation of different functions in your operations. So thanks to automatic differentiation, you don't have to do that. All you have to do is to specify your operations. Then the framework itself figure out how to calculate the gradients through automatic differentiation. And the early TensorFlow versions, especially TensorFlow version 1, supported only graph execution mode. The other execution mode of TensorFlow is called eager execution mode. Eager execution mode. And this is a newer mode. And in this mode, there are no different phases of execution. There's only single phase of execution, which is similar to other languages, such as plain Python. And this mode is useful in debugging, because when you have a statement, then after that statement you can you can examine the results of that operation corresponding to that statement. But generally, eager execution mode is slower than graph execution mode. So if you train large models, then the graph execution mode is still preferred, even though eager execution mode is nice in debugging. So eager execution mode is the default mode in TensorFlow 2. And if you want to enable graph execution mode, then you have to do it explicitly. In order to understand how TensorFlow works in graph mode, you can take a look at an example. So in this case, we consider a very simple model, which is given by this formula. So y hat is equal to f of xw plus b, where x is the input to the model, w is the weight matrix, and b is the bias vector, and f is a nonlinear function, which is also an activation, which is also called an activation function. And we consider loss function c, which is given by g of y hat and y. So this is a model. So you have an input x, and this model has parameters weight matrix and the bias vector, and the model outputs y hat, and this model output is compared with the label y, and this comparison is done by the loss function and outputs the quantity which expresses the loss, which is g, some function g of the model output y hat and the label y. So this is the example, and so this text describes different quantities. X is the input training examples, y is the label, W is the weight matrix, P is the bias vector, F is activation function, and G is the loss function. For example, we can assume that the loss function is calculating the cross entropy between the labels and the model output. So this diagram shows the computation graph of this model. So that the input to the computational graph are biases. We need B vector, and the weights, the W matrix, and the examples X, and the labels Y. So what is the first operation is the multiplication of the weight matrix and input examples. So these are the inputs, and the operations are denoted by ovals in this diagram. And after the matrix multiplication operation, matmul, you get the output of X times W. And then you have the biases, and you add the bias to the result of matmul operation. Then you get B plus XW here. Then you apply the nonlinear function. In this case, we have considered rectified linear unit to the result. So then you get the output of ReLU XW plus B. That point, and that is the model output. So I had. And then you have the labels, and labels are compared with y hat using the cross entropy function. So you get finally the loss. So this is the computational graph of this simple model. So as you can see, there are 4 operations you have to perform: so matrix multiplication operation, addition, and the real-time linear unit operation, and the cross entropy operations. And the model takes several inputs: biases, weights, examples, and labels. So this is an example, but in general, most of the models we use in deep learning can be cast into this sort of model. So what we typically do in TensorFlow is we specify the computation graph. So in creating the computational graph, typically TensorFlow do not use the actual input examples, X values here. It sort of uses a dummy example just to create the graph, because the running the example through the model or through the graph is the next phase of execution. So now we have specified a model, and a computational graph is created. So our aim is to train the model. That means that we want to pass the inputs through our model, and we want to calculate the gradients, and we want to use the gradients to update the model parameters so that the loss is minimized. So what TensorFlow does is it automatically creates a gradient computational graph or a backward computation graph based on the computational graph for the forward pass. So this is the forward pass or the forward computational graph, which is based on our specification of the model. So the mathmal add, ReLU, and loss function calculates the loss here. So TensorFlow computes the backward graph or the gradient computation graph automatically, and this is the graph created by TensorFlow. So it starts with the gradient of the loss with respect to the current variable. So at this point, the loss is, let's say it's a C, and the current variable at this point is also C. Therefore, if you differentiate C with the current variable, this your DC is 1, therefore it starts with 1. Then you have to pass through it activation function. Sorry, so this is your loss, for example, cross entropy function, and this is the inverse cross entropy function. So this gradient is passed through the dxnt, so inverse cross entropy function, and comes here. Then you have the activation function, the rectified linear unit, and you have operation corresponding to the differentiation of a rectified linear unit, and the result was like this. And you have the add operation. You have a gradient computation operation corresponding to add, and mathmal, etc. So this is the backward computation graph or the gradient computation graph. So TensorFlow can generate this graph automatically, because how to generate these gradient computation operations are built in the TensorFlow functions. Therefore, it just can use this built-in knowledge to generate this graph. So once the two graphs are available for the TensorFlow system, it can perform the forward pass by passing the input data through the forward computational graph, and then use the results in the backward computational graph, and passes the results through the backward computational graph, which actually computes the gradients of the parameters. For example, dc over db is a gradient with respect to the bias, and dc over dw, which is gradient with respect to the weight matrix. These are the two parameters. And once the system computes these gradients, they can be used in updating the parameters b and w, and so you can perform trainings. So there are several advantages of graph mode. The first one is the flexibility, because the graph is created using a general representation, which is not dependent on the API, the language you use. For example, if you use Python to create your, to specify your computational graph, the graph is not dependent on Python. That means that you can exploit the graph on different devices. Once you have created the graph, it can be used using, for example, on the language or on the platform, etc. Therefore, it is used in exporting and importing models. You create the model on one platform and use it on another. Another advantage of graph mode is that it can easily be optimized. Once you have created the graph, there are algorithms which can be used to optimize the graph. Hence, you can attain better speeds. And these sort of advantages speaks positive for the graph mode, but one of the biggest disadvantage of graph mode is that it is very difficult to debug your code in the graph mode. So as I mentioned earlier, the default mode of TensorFlow is eager execution mode. So sometimes you want to change the eager execution mode to the graph mode in order to get the advantage of the graph mode. So in those cases, you want to enforce the graph mode, which can be done using the feature known as tek4050. So tek4050 can be used directly as a function or as a Python decorator. So the code here, the first part of the code here shows how to use the tek4050 feature as a function. For example, you have a regular Python function here. So a regular function which takes several arguments and calculate the result. But if you want to use this function in a graph, so what you can do is you wrap your function with the tek4050 call. So tek4050 calls your regular function. Now it outputs a function that uses a graph. So whenever you call a function that uses a graph, is actually executed using a graph. So other way to enforce the graph mode is to use the tek4050 as a Python decorator. So this is a Python decorator. So decorators are annotated by @ character here. So decorate your function, which is perfectly regular function. And once you have decorated the function like this, whenever you call a regular function, it would be executed as a graph. So that is the way how to enforce a graph mode. So if you don't do that, the TensorFlow automatically by default goes to the eager execution mode. So a little bit about the eager execution mode, which is the default mode of TensorFlow. And this mode code is executed line by line, exactly as in plain Python or any other programming language. And since there is no graph, TensorFlow needs to record all relevant operations in order to support automatic differentiation. If you recall how TensorFlow computes the gradients automatically, or how TensorFlow performs automatic differentiation, you can remember that it does that using the recorded graph. But in eager execution mode, there is no graph. Therefore, TensorFlow needs somehow to record the operations which were performed. So therefore, in default TensorFlow mode, a new concept is introduced, which is called the tf.gradient tape. The gradient tape actually is a tape which records what happens. So whenever you perform an operation using your code, the gradient tape actually records that operation. So once you are done and you want to calculate the gradients, then TensorFlow can look at the gradients, the gradient tape, and all the operations are recorded there. Then TensorFlow can run the operations in the backward direction and compute the gradients, as it was done in the case of graph plot. So this concept gradient tape you will encounter in writing your TensorFlow code. So let us take a look at the tensors as used in TensorFlow. So not surprisingly, the main data structure of TensorFlow is the tensor, and the data structure is the data structure called tensor, and tensors in TensorFlow can be created using different functions such as tek constant. In this case, you have to specify a Python list or NumPy array as the input, or tek variable, and input should be as in tek constant, a NumPy array or Python list, and tek zeros. Then you define the shape of the tensor, and tek1s is also of the same category where you define the shape of the tensor to be created. So there are many ways to create tensors. Sometimes you create tensors directly, but sometimes you create tensors indirectly using other functions. But tensor is a generalization of a matrix. So in if you start with scalar, the scalar is a zero-dimensional tensor, and a vector is a one-dimensional tensor, and matrix is a two-dimensional tensor. And then you can extend this idea through to three-dimensional tensors, four-dimensional tensors, etc. So there can be tensors of any dimension. So here's an example where we have used the function tek constant to create a scalar tensor. As you can see, the argument is the scalar value 4. Then you have this tensor, which is a zero-dimensional tensor. And if you try to find out the shape of this tensor, you get an empty array. So this is another example where we have created a one-dimensional tensor. So as you can see, the argument to the function tek constant is a vector which has elements 2, 3, and 4. Then if you look at the shape of this tensor, you can see it has a shape of 3, and this is one-dimensional tensor. And this is an example of a two-dimensional tensor, again created using tek constant, and where you have used a NumPy list as the input to this function, and these are the values of the NumPy Python list 1, 2, 3, 4, 5, 6, and you can visualize the tensor using this figure. So it has 3 columns and there's 2 rows. And if you look at the shape of this tensor, you will get something like this: 3, 2. 3 is the number of rows and 2 is the number of columns. And this is the first is dimension 0. Dimension 0 is 3. Now dimension 1 is 2. And this tensor has 2 dimensions. Therefore, it is a 2-dimensional tensor. So this is another example of a tensor which has 3 dimensions, or 3-dimensional tensor. This is a 3-dimensional tensor, also called rank 3 tensor. So this tensor is created by calling the function TF constant, and the argument is a 3-dimensional list, or 3-dimensional. You can also use a 3-dimensional NumPy array. And so this is the first part of the array, the second part, third part, and the created tensor can be visualized in many ways. So this is the one way of looking at it, and you can see that the first part is here, this one, the second part is here, the third part is here, and it has 3 dimensions. The first dimension is the number of parts, is 3, dimension 0, and the second dimension is number of rows. This is dimension 1, and third dimension is dimension 2, or third dimension is the number of columns. So this is one way of visualizing it, but if you examine the shape, you can see that shape is 3 to 5, corresponding to dimension 0, dimension 1, dimension 2. So this is another way of visualizing it. When the third one is another way. But I recommend to use this visualization because it is more consistent with the matrix visualization, and in this case dimension 0 is the number of columns, and dimension 1, which is also the dimension 2, is the number of rows. Try it again. So this is the first dimension, now dimension 0 is the number of rows. And then this is the second dimension, or dimension 1, and this is the number of columns. So this is the third dimension, or dimension 2, and this gives the number of slices, or it can be number of channels, for example, in an image, or it could be the depth. So very often when we talk about images, we call this dimension 0 as the height, h, number of rows, and dimension 1, number of columns, as the width, w, and third dimension, or dimension 2, as number of channels, or depth, d. So this is the visualization I recommend to use in dealing with tensors. So this is yet another example of a tensor. In this case, we consider rank 4 tensor, or a 4-dimensional tensor. And in this case, the tensor has been created using this function, t of zeros. In this case, we specify the dimensions directly, not the contents. So this is the dimension 0 and dimension 1, dimension 2, and dimension 3. So this is a 4-dimensional tensor since it has 4 dimensions. And also we call tensor rank 4. And dimension 0 has the corresponding axis 0, dimension 1 has axis 1, etc. So this tensor can be visualized using this picture, and dimension 0 is this, and dimension 1 is this, and dimension 2 is this, and the last dimension is this, dimension 3, or the 4th dimension. So if you look at the first dimension, or dimension 0, it is actually, it can be interpreted as the number of images. If you are talking about image processing example. So this is the number of images, for example. So this is typically denoted by n, which actually indicates how many images are there in your tensor. So this tensor, for example, can represent a whole batch of images. Then this is the first image, this is the second image, this is the third image, etc. Then the first dimension, or dimension 0, represents the number of images in your batch. And the second dimension, dimension 1, represents the number of rows in each image. So this is actually the number of rows, or the height h of each image. This is the second dimension. And the third dimension is dimension 2, and it represents the number of columns, and it is the width of each image. And the last dimension, dimension 3, is the number of channels in each image, or should be called, let's call it D, the depth of each image, or number of channels. So if we consider a 4-dimensional tensor which represents a batch of images, so the first dimension gives the number of images in the batch, the next dimension gives the height, the next dimension gives the width, and the last dimension gives the depth, or the number of channels of the images. So we usually call it NHWD format. So that means that in this format, the first dimension gives number, second dimension gives the height of the image, of each image, and third dimension gives the width of each image, and last dimension gives the number of channels or depth of each image. So this is the default format of TensorFlow, NHWD. So this is a little bit different to the format used in PyTorch, for example. In PyTorch, the format is NDHW. So this is the PyTorch format, and This format is not used in TensorFlow. So now we have come to the main part of this lecture, namely how to create a model with how to create a deep learning model with TensorFlow and how to train it. So main steps in training a deep learning model with TensorFlow are listed in this slide. So first of all, we have to define the model architecture. So this is the first one. Then we have to define the loss function. Then we need to choose an optimizer and a learning rate, of course. Then we need to create the data feeding code. Finally, we have to write the training and validation loop. So in the training and validation loop, we have two main parts, the training step and the validation step. In the training step, we run the next training mini batch through the model. Then we calculate the loss for the examples in that mini batch. Then we calculate the gradients and update the model parameters for that batch. And finally, update the loss and metrics summaries just to inspect how the training goes. So this is the steps in the training sub-step. And in the validation step, we again run the next validation mini batch through the model. We have a separate set for validation, and we take a batch from that set and run it through the model. We calculate the loss, and we update the loss and metric summaries and save them to inspect how the validation performs as the training goes on. So in the next slides, we look at each of these steps in a little bit more detail. The first step is how to define the model architecture. In TensorFlow, we create a model by combining or by attaching a set of layers together. So in this part, we look at how to create layers. In the next part, we look at how to combine layers to create a model. So typically in TensorFlow, we create layers using the functions available under tek4050layers. We can use either predefined layers, such as tek4050layers.layers.con2d, in case we are interested in convolution, two-dimensional convolution layer, or tek4050layers.layers.dense, in case we are interested in a fully connected or dense layer, etc. So there are many predefined layers to choose from. So you can make use one of them to define the layer you are interested in. Or we can create custom layers. Custom layers can be created by extending this abstract layer. So this is tf.keras.layers.layer. So if you want to create a custom layer of your own, then the way is to extend this abstract layer. we will take a look at some predefined layers. So this is one of them, which is a two-dimensional convolution layer, or Con2D, so which is defined under the package tf.keras.layers. And if you call this function, you can create a two-dimensional convolution layer. There are many arguments with which you can sort of tailor that layer to your needs. So even though there are several arguments, usually you need to define the first 3 or 4 arguments. Of course, you need to define the number of filters you need. For example, 64, something like that. Then you need to define the kernel size or the filter size. So it could be a single integer, or 3, or it could be a tuple, so 3 by 3. It's a filter size that you are going to use, and the strides. The strides that you're going to use when you perform convolution, it could be a single integer, which is common to all directions, or it could be a tuple, in this case 1 by 1. So stride 1 in x direction and stride 1 in y direction. Also, you can define the padding strategy, the zero padding strategy. So you can either use the valid padding or the same padding. If you don't want to reduce the number of dimensions of your output, then you can use the valid option same. If you don't mind what happens at the output, then you can just use the padding option valid. So in addition to that, there are many options, such as how to initialize the layer, how to initialize the bias, and how to initialize the weight matrix, and is there any regularization you need to incorporate, etc. So we can take a look at the TensorFlow API description side for more details. So another predefined layer in TensorFlow is dropout. And a dropout is a regularization procedure, but in TensorFlow, it has been defined as a layer. So, for example, if you have a dense layer, dense layer, or CNN layer for that matter, then you can add a dropout layer here after that. Then this dropout layer will apply dropout to the output of the previous layer, in this case, a dense layer. So for defining dropout, you can use the tf.keras.layers.dropout, and only argument you can specify is the probability with which neurons are dropped out. So in this case, we have 0.5. That means that for each neuron with a probability of 0.5, you either use it or not. So the other lines shows the output of calling a dropout layer for this input. So it's worthwhile to observe a few things here. First of all, so this line where we call tf.keras.layers dropout is used to create a dropout layer. So dropout, the output is the layer itself. This is the layer itself. Then lines 4, 5, and 6 we actually call that layer with inputs. So this is the creation of the layer, and this is the use of that layer. So we call the created layer with the input and other argument which tells the layer to behave in the training mode or in the non-training modes. If the training argument is true, the training so the layer behaves as it is in training. If the training argument is false, the layer behaves as it is in testing. So the dropout layer has different behaviors in training and testing. So that can be controlled using this argument. So generally, when you use built-in layers, then you first create the layer with a set of arguments which are used only in creation of the layer. Then you use that layer with a set of arguments which are used only in using that layer. So you have to differentiate that two stages, creation and use. And the more specific to this dropout layer is here that, so this is the input, this, and dropout layer randomly drops certain outputs based on the probability specified here. And at the same time, it scales up the outputs which are not dropped. So in this case, for example, you can see that the first output has been dropped. So here we have 1, but the output is 0 here. The second output 1, it has not been dropped, but it has been scaled up using the factor 1/1 minus 0.5. So this is actually 2. So this value has been scaled up. And the third one is 1, but it has been dropped out, and you have 0, etc. So these two are for training, and you can also observe that outputs of calling dropout, these two cases are different. So this is a random operation. So if you call it another time, you get a different output as well. And when you call it in the testing phase by setting training as false, it actually does nothing, just copies the output, so input to the output. So input is 111, 111, it has been copied to the output. So it does nothing in the testing phase. This is yet another example of a built-in layer, so batch normalization. Batch normalization is a regularization technique, but it is available as a built-in layer in Keras. So this is the function you want to call to create a batch normalization layer, tf.keras.layers.batch normalization. And there are several arguments you have to specify. The first argument is along which axis you want to create normalization. So it is typically the last axis, the channel axis, and you normalize the batch over all other axes. And the second argument is center. That means if you remember the formulae for batch normalization, this is corresponding to beta, and this is scale, this is corresponding to gamma. So if you can take a look at the formulae for batch normalization, you can observe these quantities, and these arguments tell to the layer whether to use beta or gamma. So if it is true, use a beta value and you train value for beta. If the scale is false, then you do not use gamma and vice versa. Also, there are many other arguments which you can use to customize the batch normalization layer according to your needs. So please refer to the reference page of TensorFlow for more information. And so the line 1, you have created your batch normalization layer, and line 7, you have used it with an input X and a flag indicating whether the layer is used in training mode or testing mode. In this case, used in training mode, and in line 8, batch normalization layer is used in testing mode. So as mentioned in the previous lecture on convolutional nets and supervised learning pipeline, layers such as batch normalization and dropout have different behaviors in training and testing. So you can specify in which mode you are going to use that layer depending on the phase.